Dimitri Montgomery, and this is the research I've been conducting on malware detection with the use of locality-sensitive hashing under the supervision of Professor Adogan. The main goal and motivation behind this research is to find a new way to efficiently detect malware, which have become more persistent and constantly evolving with threats such as ransomware, Trojans, and worms, and etc. Many malware threats often reuse code, and newly created threats are just often variants sharing the same malware DNA. Being able to detect code similarity allows us to catch new threats quickly and efficiently. In this project, we utilize a method called locality-sensitive hashing for malware clustering that focuses on meaningful behavior through the use of large language models. And instead of scanning syntax, we use these large language models to describe what the malware does and apply a min hash function and locality hashing to group similar behaviors. When we actually convert the source code into English explanations, we are enabling behavioral comparisons through files without having to rely on static signatures from the actual malware code. This allows the detection of malware DNA, which efficiently clusters similar threats for quick detection even in massive data sets. Some of the key concepts that go along with this project include the use of large language models, which we tested, such as Gemini, GPT-4, Claude 3, and DeepSeek, which are used to actually narrate the malware behavior and actions. Additionally, we convert these summaries into shingles and turn them into min-hash fingerprints, which are eventually used in the last step of the LSH model. We also group similar files using the LSH, and we avoid all versus all comparisons, which are comparing each pair of files to each other, which eventually over time can become computationally expensive. And why does this actually matter? Well, it's because we become resilient to code obscurity and language differences. It enables scalable behavior-based detection, and it makes malware readable and clusterable for easy search. And our goal through this research is to create an efficient and scalable method of grouping similar malware for faster and more robust threat detection. So what are actually some of the common challenges in traditional similarity detection methods? One of the main issues with traditional detection methods is the fact that in large datasets, these methods compare every possible pair of file with each other, which become costly and impractical over time, which is the all versus all comparisons, which we want to avoid. Some of the common methods include techniques like the k nearest neighbors, KNN, cosine similarity, and Jacquard similarity, which require each new file to be compared with all others, which is computationally expensive again. This again makes the need for an efficient strategy for similarity detection needed when current methods are impossible to scale to modern malware with millions of files. And as you can see on the right side, these are different similarity detection methods and models. So what actually is locality-sensitive hashing? Locality-sensitive hashing, or LSH, is a probabilistic algorithm that can quickly group or bucketize similar items without actually having to compare every new file or pair of files in the dataset. What makes this algorithm probabilistic is the fact that we can get different outputs from the same set of data, which we will see in the min-hash process. To actually bucketize similar items, LSH doesn't need to compare all files, but instead hashes each file or item so that items that are similar will be placed in the same bucket. This again allows for quick and efficient searching of similar items, which can reduce the number of comparisons, making it great for large data sets. And again, the core idea is if two items are similar, their LSH generated hashes are likely to be similar, so they end up in the same bucket. And the main advantages is that this avoids all versus all comparison again, and it's scalable. It works with millions of samples. Some of the history behind LSH before we move on to the actual process and how this algorithm works is this algorithm was developed in the late 1990s by Andre Z. Broder, a researcher at the company Alta Vista, with the goal of detecting near duplicate web pages. This research was the foundation for a scalable way of detecting similar items and played a role in the creation of applications such as plagiarism detectors, clustering of documents, image and audio similarity, and for this specific research, malware detection. His first publication was called Identifying and Filtering Near Duplicate Documents. And a little expert from his actual research paper is quote, the algorithm for filtering near duplicate documents discussed here has been successfully implemented and has been used for the last 3 years in the context of the Alta Vista search engine, where he would then reveal his process behind the LSH process. Our very first step in our LSH algorithm is the shingling process. This step's role is to convert a file's contents into a set of overlapping substrings of size k, which we have the power to toggle, and that has a large role in how the file's contents are interpreted in the hashing process. This process can be at a character level, word level, and as well as a token level, allowing us to capture the local context and order of our file's contents. This step is important as it allows for set-based similarity capturing the file's features and prepares us for the future step of hashing. Some examples include the character, word level, and token-based hashing. As you can see in the character level shingle, our string is malware and our k value is length 3. So in our set of substring shingles, each substring is split into 3 characters and so on. The next step in our algorithm is using the min-hash method. This method takes a set of shingles and turns it into a signature through running many different hash functions of the same set on the same set of shingles and storing the minimum hash value for each function applied. This acts as a fingerprint for the file used to identify its features, and the more documents actually match with each other, the more information, often those minimum kept values from the min-hash process, will match. This allows us to estimate file similarity without the need to compare every shingle from each file to one another. And going back to our k value that we set in the shingle process and how it can affect the hashing process, you may use the same document with size 5 shingle and hash it, but if you change the size to say k equals 10, then the hash value will be different, which can affect the outcome of similarity. The key property in this step uses Jacquard similarity through the fact that the chance documents have the same min-hash is equal to the Jacquard similarity being the intersection of the sets divided by the union of the two sets. As you can see in this image right here, the first image, the Jacquard similarity is equal to the intersection of two sets divided by the union of two sets. This means that files that are near similar would obviously end up having similar min-hash values, because if both files have a shingle that is exactly the same, then the hash function applied to said shingle should be the same. And again, in the second image, you can see the min-hash of one set is equal to the min-hash of another set, which is equal to their Jacquard similarity. Finally, the last step is to actually apply the LSH bucketing and group similar items. Once the min hash signatures are created, we then divide all signatures into bands. These bands are then sent to a defined set of buckets, and if files share a bucket within any band, they are considered candidate pairs and used for further comparison. This is great because it can reduce comparisons from billions to just a handful depending on the size of your data set, and allows for large-scale similarity detection. The key steps in the LSH bucketing is banding. We divide min hash signatures into bands. For example, a min hash signature of 100 can be divided into 20 bands with 5 hash buckets. Next, we hash each band. Each band is hashed into a bucket. Documents with matching bands go into the same bucket. And lastly, the candidate pairs. If two documents share a bucket in any band, they are considered candidates for detailed comparison. And as you can see in this image, data that is closely related to each other, like the pink group, blue group, and green, are sent to buckets where we can eventually look inside and get different similarity numbers from different files. So some of the main tools and libraries and functions I incorporated in my Python implementation of the algorithm. Some of the main objects I used were found in the data sketch library, like the minhash and minhash LSH objects. One of the main functions we made was called get k shingles, which returns a set of overlapping characters of size k, where a minhash function would then apply 128 permutations on that set. Our LSH threshold variable, which we're able to toggle to get the best results, was set to 0.25, which meant that files needed to be 25% or more similar to be placed in the same bucket. Some additional libraries we used was the OS, collections, and time, just to get more data on our actual model. And the main parameters were the k shingle size, number of permutations, how many hash functions we applied in our min hash function, and our threshold. Now, just to get a rundown of the main steps of LSH, we should go over the LSH pipeline, highlighting the important steps. We first pre-process and get our algorithm ready by translating our malware code into English text. We then begin the shingling and breaking down each description into overlapping substrings. Next, we generate our minhash signatures from our set of shingles, then insert each shingle or each signature into the LSH index for fast searching. When a new file arrives, we compute its minhash and query the index for similar items. Lastly, we report and review the candidate pairs for deeper analysis. And a code snippet from my actual model is on the left, the generate minhash function, which takes our actual text that we translated from the large language model and our number of permutations, which we have set to 128. It starts off by setting a variable which calls the get k shingles function, which just returns a set of shingles from that English translation. Next, we set a function m, which is just setting our minhash signature. Lastly, we have a for loop, which goes through each of our shingles and updates the minhash signature with the lowest minhash value from each permutation that we apply to it. So we will have a minhash signature of 128 values, including the minimum values from each iteration. So what are some of the main advantages and limitations of this approach? This algorithm and strategy allows for extremely fast and scalable similarity search, which makes it possible to practically analyze large datasets of malware for code reuse or cloning. While this can be extremely powerful, the accuracy of the algorithm highly depends on the set shingle size and what threshold you choose to define similar items. This is important to prevent false positives and negatives. The advantages, again, fast, scalable, language agnostic, and tunable. The limitations is that it needs good translation shingling and a comprehensive database. And as you can see in this image on the bottom right, it goes through the main steps of the LSH process. The shingling, which we get substrings of size k. The min hashing, we get short integer vectors that represent the sets. And then lastly, we collect our candidate pairs using LSH. Some of the trial and error learnings I've had after working on different models and taking different approaches is that this project required me to test out different methods to reach a defined and reliable model, while also uncovering certain LLM limitations and system design problems that were eventually resolved. The testing of different large language models to find the right one revealed restricting behaviors, consistency of outputs, ethical filtering, and prompt sensitivity. Even within the LSH process, we came across problems such as similar items landing in different buckets, even if they were the exact same malware file before, due to slight translation differences. This would highlight the importance of large language model determinism and output normalization, the actual output difference of the LLM based off of what you have or what you gave it. The main key issues and some of the fixes that we had was that Gemini failed initially, but it just simply required me to activate the Google Cloud product activation. Next, Claude blocked out output, which was resolved with academic styled prompts, but Claude was pretty hard to get any description back. Another issue that we had was duplicate translations occurred, which we fixed by checking existing file names and content hashes. Some of the main insights that I gathered through this project is that LSH is actually approximate, and it should be mostly used for fast filtering, and that it's not exactly perfect for grouping, but that can eventually change based off of our toggling of the K value and thresholding. Next is that translation output consistency affects shingle stability and min-hash similarity. Again, if we have two exactly same malware files that we put through the LLM translation, it's not going to be exactly the same, which will result in different shingle values and, again, min-hash values. Lastly, behavioral similarity is strong, but it needs to be normalized summaries to be reliable. Again, like I just said, if we have two exactly same malware files and we put it through the LLM, it's going to give slightly different outputs, and so we need to find a way to normalize these summaries so that it's more efficient. My final takeaway from this research, in ways that it can be greatly improved, the approach of getting large language models to translate code shifts detection from the importance of syntax to the importance of semantics and the meaning and behavior of the language. Through the use of LLM summaries with hash-based similarity, we can create a scalable algorithm for grouping threads even if they are not directly similar at the code level. I found that Gemini 1.5 Pro was the most effective for this project due to its fast performance, structured output, and translation. Handling malware summaries quickly without redacting the content, which made it great for min-hash based clustering. Some of the main highlights for Gemini was that it was able to translate files in roughly less than 20 seconds on average, which was faster than GPT-4 and DeepSeek, which averaged about 45 to 60 seconds. Next, it maintained consistent phrasing across batches for reliable min-hash signatures, meaning that um, the files that we uploaded, they were pretty consistent and they didn't vary off and go into a different direction. It produced clear, structured summaries without excessive verbosity, without a lot of wordiness, just getting straight to the point and describing what the malware is efficiently. It also identified malicious behavior without censoring or blocking issues, which again wouldn't be very helpful, and is the same problem that we ran into using Claude. What's next? We could add pickle support to actually save and load the LSH buckets. We can build a user interface to view the actual malware buckets, and we can label these clusters by malware family types, such as ransomware, worms, and etc. One of the main fixes and ways we can make the similarity detection more efficient, though, and accurate, is to actually edit our prompt that we give to the large language model for malware summaries to include a malware type identification paragraph, which details the specific type of malware, such as ransomware, Trojans, etc., and what it's commonly used for to increase the similarity percentage of similar files in the min-hash process. And a final quote that essentially summarizes my approach to the LSH based similarity detection is that this LSH pipeline doesn't necessarily detect code, but instead detects behavior, which means that through our summaries we get from our LLMs, we are really detecting the similarity of the behavior of the malware rather than its actual code. And with that comes to the end to my presentation. Here are my references I used to compose all of my information. I hope you enjoyed my presentation, and I hope you were able to learn something new today. Thank you. Something else that I wanted to include were possible revisions that I thought we could add to the current research paper that we could have, which is what this whole project is based off of. I'm going to give rough summaries of each section that I decided to add, but feel free to pause it and read over the actual revisions that I proposed. For the first section, I labeled it LLM integration for meaning-based translation, which could possibly be added to section 3 or become a subsection of the current section 3 proposed work. This part is about how we use AI language models to turn malware code into plain English before analyzing it. And instead of comparing just to raw code, we wanted to compare what the malware actually does, the behavior. We tried a few different large language models, but Gemini ended up becoming the best fit because it was quick and gave us clear summaries. We broke those summaries into small chunks and then grouped similar behaviors together using hashing. So we basically shifted from comparing lines of code to comparing what the code actually does in its behavior. Next is an expanded paragraph for section 5, the results, or section 4, the results. In the results, we saw that our system didn't make the mistake of flagging normal code as malware. It only grouped things together if they actually acted like malware, and the whole process was really fast. It could turn hundreds of lines of code into useful group data in less than 20 seconds. And overall, using Gemini to translate and then clustering based on behavior worked really well. It can make future malware detection even better. And this is just another proposed section. Lastly, another section that I think we could add or possibly fit into the research paper is an LLM comparison and Gemini selection rationale, which can be added before Section 5, the conclusion, or possibly fit into Section 4. This section essentially just explains why we picked Gemini over the other large language models and how we tried Claude, GPT-4, and DeepSeek, but they were either too slow or blocked too much content. And Gemini was the fastest and most consistent. It gave us detailed summaries without blocking important stuff and made it way easier to group similar malware. That made our system more accurate and practical for real world use.